Okay, so we are going to cover section 3.5 today. And for those of you who are joining us through Zoom, we're having issues with, I don't know if you've noticed, but Pearson is timing out. And so I'm not able to access Pearson today, or I can, but it's very slow. And so I've just prepared a few example problems from this section to work through. And so those of you who are Zooming, I'll just give you attendance credit. So I have Thomas here and Ansley. So you have a credit for attending today. And we just won't be able to work in MyLab. So this section covers optimization problems. Basically what you have in these type of problems is you have an objective function that you want to either maximize or minimize. In this example, we are going to minimize our Q function. And this Q function is called the objective function. So in these problems, you typically have an objective function, and then this is the constraint. Without the constraint, we wouldn't have a maximum or minimum value often. So a lot of these problems have a constraint. Now, every now and then you have a problem, and I will do an example today where the function itself has a maximum value, and so you don't need a constraint, but often you need this constraint. So, because obviously this function has no maximum or minimum, you could just, any X or Y that you put in there, you can always find a larger X or Y to substitute to. Anyway, I guess this function we're trying to minimize, but so when you're doing these problems, notice we have two variables here. So the constraint, which is also expressed in two variables, is used to solve for one variable and then substitute in your objective function. So with X plus Y equal to 10, I'm going to solve for Y by subtracting X from both sides. And so Y equals 10 minus X. And then I'm going to take this Y and put it in this function. So I get that Q is now going to be equal to 3x squared plus 7. And instead of having Y squared, I'm going to put 10 minus X in place of the Y and square that. So now we have a quadratic function in one variable, and so we can go ahead and find the minimum value. First, I'm going to FOIL this out. So I get 3x squared plus 7 times 100 minus 20x plus x squared, like that. Okay. This is just the FOIL, using the FOIL method on this perfect square here, which is a perfect square binomial. And then I'm going to distribute the 7 through now. So I get 3x squared plus 700 minus 140x plus 7x squared. And now I can combine like terms. So we have 3x squared and 7x squared. So that gives me 10x squared. And I like to put it in descending order. So here's the x squared term. Now I'm going to put the x term. And then finally the constant being 700. And we can go ahead and divide out by 10. Notice that each term has a common factor of 10. So this is going to be 10 times x squared minus 14x plus 70. And we're going to go ahead and take, at this point now that we have a function that we're working with, We're going to go ahead and take the derivative to find the max, or I'm sorry, the minimum value. And of course, the 10 is not going to change anything. So here we have 2x minus 14. And if we set this derivative here equal to 0, obviously 10 is never 0. So in order for this product to be 0, 2x minus 14 must equal 0. So we get that if we add 14 to both sides, 2x is equal to 14. And then I divide both sides by 2. And finally, I get that x equals 7. Then x equals 7, remember, now we can use this answer to find what y is. Y is 10 minus x, but we showed that x was 7. So plugging this in here, we get that y is 10 minus 7, or y equals 3. So the solution to this optimization problem is just x equals 7 and y equals 3. That's my solution. So this will give me a actually minimum value. I keep saying maximum. In this problem, we're finding the minimum value to this function right here. Okay. And this was taken directly from your homework or something very similar to it. So there are some problems like this in your homework where basically you're given an objective function and you're given a constraint, and you need to find the derivative of the objective function after substituting, because you can't find the derivative with two variables. I mean, you could do a partial derivative, but that wouldn't work in this situation. So you use the constraint to solve for the other variable and plug it in, and then take the derivative, set it equal to 0, and that's how you get your solution. Any questions on that one? Okay, that's kind of an abstract problem, not really very interesting. Here's a real world problem that we're going to do now. This also, I think there's a homework problem like this. I'm pretty sure, very similar to it. So I extended, oh no, wait, you don't have your homework due until Thursday. I was thinking of my other class that has homework due tonight. You may have noticed that there are problems with the MyLab Math, and that's why I'm not using the in-class assignment. And I see you just joined me, Frank, so I'm going to write you down on the attendance so you don't have to worry about doing the assignment. I'm just working through example problems. And here we have a farmer that is constructing a pen, and this wall is, there's some sort of building like a barn or something. So this side does not need fencing because it's a wall, but he wants to construct a pen that has it's subdivided like this, and then it has a length and a width, and he has 600 meters of fencing. So he wants to maximize the area of that pen that he's building, given the constraints. I suppose the wall is a fairly large, I suppose it's a large building, and so obviously you can't change the dimension of the wall, but I'm assuming that the wall is going to be larger than the pen so that you don't have to worry about that. Okay, so we have an area that we want to maximize, and normally, if you didn't have a constraint, there would be no maximum. But because we have this 600 meters of fencing that we have to, as a constraint, then we know that this function will have a maximum value. And so, first of all, I need to find the area function. That's simple. That's just the length times the width. So the area is going to be xy. And then the constraint, this is my objective function that I want to maximize. It's always the function you want to maximize or minimize as your objective function. And my constraint is that I have a limited amount of fencing, 600 meters to be exact. So I'm going to have this side is X, this side is X, that's 2X. And then I have 1Y, 2Y, 3Y. I don't need one for the wall. So I have plus 3Y, and that's going to be totaling 600 meters of fencing. So I want to solve for Y here, let's say. You could do X, but it doesn't matter. You'll get the same results. I'm going to subtract 2X from both sides to get Y by itself. So on the left, I have 3Y, and on the right, I have negative 2X plus 600. Then I want to divide both sides by 3. And so that gives me Y equals negative 2/3 X. And then 600 divided by 3 is 200. So plus 200. So now I'm going to take this Y and substitute it into my objective function. And that will give me that the area is X times Y, which is negative 2/3 X plus 200. Okay. And so now I have this function. I'm going to go ahead and distribute this X through the parentheses. So my area function now is negative 2/3 X squared plus 200X. Now at this point, this is what I want to maximize. So notice it's a quadratic with a leading coefficient that's negative, so it's going to have a maximum. It opens down, and it's a parabola that opens down like this. So here's the maximum value. Now I can use calculus or algebra to solve this, because we know that because it's quadratic, the vertex is the point of the maximum. So, but I'm just going to do calculus. So I take the derivative. I get negative 4/3 X plus 200. I'm going to set this equal to 0. And so I get negative 4/3 X plus 200 equals 0. And I subtract 200 from both sides. Then I'm just going to multiply both sides by negative 3/4. That will give me 1X on the left. And on the right, it'll give me 150. So I get that X equals 150. And since X is 150, Y is going to equal negative 2/3 times 150 plus 200, which is negative 100 plus 200, which is 100. So the solution to this problem is that the length for the farmer's fencing, the length of the pen, if you will, is 150. And the width, and that's in meters, of course, and the width is 100 meters. All right, so it's a fairly lengthy problem, but it's mostly algebra, you know, just substituting and solving. The main thing you just know is that when you're maximizing or minimizing, you just set the derivative equal to 0 and find that X value. And then once you get the X, then you can find the Y. Any questions on that one? And like I said, I'm pretty sure this is in your homework. So you have, or something very similar. Here's another one. I did this in my class earlier, so just to save myself the trouble of drawing a picture again. What I've got here is I've got a package that's being sent through the Postal Service, and it's got a length, and then it has a square for the girth, okay? The girth is the distance around the box like this. So the girth is X plus X plus X plus X. And then you multiply, or then you add the length to that. That constraint is 84 inches as specified by the Postal Service in this problem, okay? So that's the situation. Let me go ahead and do this on another sheet of paper, clean sheet here. So we have the length plus the 4 sides of the girth. That's has to be 84 inches or less, but we want to maximize. So we're going to use all the 84 inches as we can. And we want to maximize volume. Say a company is shipping out a product and they want to maximize the volume of their box and get their most in it that they can. So the volume is the length times the width times the height. And in our example, let's go back to the box here. The length is Y, the width is X, and the height is X. So the volume is Y times X, or X squared Y is our function. But we don't want to function in 2 variables. So I'm going to take my constraint and solve for Y. And that means that Y is 84. I'm going to subtract 4X from both sides. And then I'm going to substitute this new Y here is going to be replacing the Y in my volume. Okay. So now the volume is just a function of X, and it's going to be X squared times 84 minus 4X. Okay. I'm going to go ahead and distribute that X squared to the 84 and to the negative 4X. And this is the point when you've simplified it enough to go ahead and take that first derivative. And 2 times 84 is 168. X minus 3 times negative 4 is negative 12X squared. I'm subtracting 1 from the 3 in the exponent there. I'm going to set this equal to 0. And it looks like I can divide both sides by 12, right? 168 has a factor of 12. So I'm just going to go ahead and divide both sides by 12. And I get, let's see, this will be 14 minus X squared. 14X minus X squared equals 0. And at this point, I want to factor this quadratic. Notice that I have a common factor of X, so I can take X times 14 minus X equals 0. If I set each one equal to 0, subtracting 14 from both sides gives me negative X equals negative 14, or if you will, X equals 14. So this is the correct solution. Why does 0 not work? Well, think about it. Think of it in the context of the box. You don't want to have a box with 0 length and 0 height, right? That wouldn't work too well. So this is not a valid solution, but 14 sounds good. And if X is 14, then remember Y is 84 minus 4 times X. So Y is going to be 84 minus 4 times 14, which is 84 minus 56, which is going to be 28. So these are the dimensions of this box. It's going to have a height and a width of 14, and then it's going to have a length of 28. That will maximize your volume given the constraint of 84 inches. And so all of these problems are pretty much like this, where you have a function in 2 variables or more, and then you've got to eliminate variables until you just have 1 variable left, like we had an x here. Then you can go ahead and take the derivative and get your values. Any questions on that one? Okay. Another problem from your textbook is involving a company is selling suits, okay? And the price function that to maximize their profits, they found that if they set the price at 150 minus 0.5x, this is the price per unit, they'll maximize their revenue that way, and X is equal to the number of units sold. And I think they have to be produced and sold. So you have to sell all of your units that you produce. And this is going to maximize revenue. They figured this out. Now, the question is, what is the revenue? Well, the revenue function, that's part A, is R of X, is found by taking the price per unit, multiplying it by how many units you're selling. So it's going to be X times 150 minus 0.5X. So this is my revenue function. And I want to go ahead and distribute the X through. So it's 150X minus 0.5X squared. That's my revenue function. The part B wants to know, what is the profit function? And I'm going to use a capital P. I already used a little p for price. Now I'm going to use a capital P for profit. To calculate the profit, you take the revenue minus the cost. So it's going to be R of X minus C of X. And this is the part I forgot to write down. In the problem, they give you the cost function. So I should put that up here along with the information that's given to you. And that cost function is 4,000 plus 0.25x squared. So we're taking the revenue that we calculated in part A, and we're going to subtract the cost. Now be careful here. The cost is 4,000 plus 0.25x squared. You need to subtract the whole thing. So it's really important to have those parentheses in there, and then you're going to distribute that negative. So be careful with that. That's a common mistake. And so we have the leading term is negative 0.5 minus 0.25. That's negative 0.75x squared. The middle term is 150x. And the constant term is negative 4,000. So this is my profit function. And in part C, they want you to find out how many units do you need to maximize profit? And how many units do you need to produce and sell? And that would be when the derivative of this function is 0. So taking the derivative, I get 2 times negative 0.75 is negative 1.5x squared plus 150. The derivative of 150x is the 150. The derivative of negative 4,000 is 0. And now I set this equal to 0 to solve it. I shouldn't have a 2 there. Remember, when you take the derivative, you subtract 1 from the exponent. So I made a mistake there. Now solving this, I'm going to subtract 150 from each side, and I get negative 1.5x equals negative 150. Now I can divide both sides by negative 1.5. And that's going to give me x equal to 100, right? Negative 150 divided by negative 1.5 is going to be positive 100. So this number of units produced and sold is going to give me the maximum profit. Now the question is, what is that profit? Well, you just have to take that 100 and plug it into your profit function to find the profit. And here is the profit function. So I get P of 100 equals negative 0.75 100 squared plus 150 times 100 minus 4,000. So this is going to be negative 0.75 times 10,000 plus 150,000. Oops, 15,000. I had an extra 0 there. I've got 3 zeros, so it's 15000, and then minus 4,000. Probably should have just used the calculator to do this, but that's okay. We're almost done. So we have 15,000 minus 4,000. That's going to be 11,000. And then here I've got 4 zeros. So I have 7,500 like that, minus 7,500. So the answer is $3,500 is my profit. And what is the price that you have to set to get that profit? Well, remember, this P is my profit function. Little p is my price function. So little p of 100 now is going to be, here's little p, 150 minus 0.5x. That's given to us in the problem. So I'm going to plug in 150 minus 0.5 times 100, and that's going to be the price that I should set is $100 per suit. We're selling suits in this problem. Okay, so this has got quite a few parts to this. They give you the revenue, or no, I'm sorry, they give you the price per product per unit. The number of units is X. You multiply those to get the revenue. They give you the cost function. You subtract the cost from the revenue to get the profit. Then you set the derivative equal to 0 to find the number of units that need to be sold, produced and sold to reach that maximum profit. And then what is the profit? Well, you just plug the 100 into your original function to get 3,500. And then what's the price? You plug your 100 into the price function to get that $100. So, any questions on that one? That's all I have for you today. So if we have some extra time, if anybody has any questions that they want to go over, unfortunately, I don't think we have access to the software. But don't worry, for those of you Zooming, I do have you recorded here down as attending. So you will get full credit for attending. And if there aren't any questions, I'll just see you next time on Wednesday. Anybody have any questions? Okay, well, have a good one. And we'll see you on Wednesday.
Thank you.
You're welcome.